Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. In this video, I am going to explain example 4.4, and as you can see in this figure, you have a two liquid surge tank in series. You have tank 1 and tank 2, and then you have QI, which is the volumetric flow rate that comes into tank 1. Okay, and then you have a valve with a resistance R1, and the outflow from tank 1 is Q1. H2 is the level in tank 2, and then you have a resistance R2 representing the resistance in the valve at the outflow of tank 2, and you have Q2, which is the volumetric flow rate that comes out from tank 2. Okay, so in this problem, what they want you to do is to get the transfer function that relates the output Q2 to the change in input QI. So how are we going to do this? Okay, we need to find the transfer function that relates all of these variables. Okay, so first of all, the thing that we need to do is we need to derive the dynamic model. So this question, they already give you a head start where you can actually use equation 2.56 and 2.57. But if you don't want to do that, you want to start from the beginning, it is better actually. When you see here, you have a level. Okay, you have height, which is the level of the tank. So as we have discussed before, when we have a level, we can use the mass balance equation. So let's start with tank 1. For tank 1, so from mass balance, we know that the density multiplied by volume, the change in that is the mass, and this is equals to rho QI minus rho Q1. Okay, in minus out, and this is accumulation. Okay, all right. So we can assume that density is constant. Assume that rho is constant. So that will give you your equation rho dV dt equals to rho Qi minus rho Q1. So we know that we can cancel the density. And then we also know that volume is equals to cross-sectional area multiplied by height. Okay, so we can actually have our equation in terms of these two. So we have d a h1 dt, let me put this in bracket, equals to qi minus q1. Okay, so this is a1, the cross-sectional area for tank 1, and we know that the cross-sectional area is actually constant, so you can bring that out, and the only thing that varies is just your height, qi minus q1. So let's put this as equation number 1. Okay, right, just clean this up a bit. Okay, and then let's use the equation from the resistance of the valve. So you have another equation. From the equation of the resistance of the valve, because the resistance is given there. Okay, what you have is Q1 is equals to 1 over R1 multiplied by H1. This is equation number 2. Okay, this equation you get it from equation 2.57. And then what you do next is you substitute 2 in 1. So what happen is you will have A1 dH1 dt equals to Qi minus 1 over R1 H1. Okay, so this would be your equation number 3. Then we go to our next step. Once you get the dynamic model, you need to find your steady state value. Okay, so this is your second step. Evaluate equation 3. Evaluate equation 3 at steady state. Okay, so when you evaluate at steady state, we are saying that the left hand side is 0. So the rest will become at nominal value. This is H1 prime. Okay. And then the third step is for us to identify our deviation variables, or we put our equation in deviation variables. So when you put in deviation variables, you can see from equation 3 and equation 2, you have Q1, Qi and H1. So these are the variables that you need to put in deviation variables. Qi is actually Qit minus Qi bar. Next, I would have Q1 T equals to Q, this is prime, the deviation, this is Q1 bar. And then I would have H1 prime equals to H1 of T minus H1 bar. And don't forget, you have this term here, your derivative, it would be dH1 prime, you don't have to put the T if you don't, dt equals to dH dt. So next thing you need to do is we need to put the equation in terms of deviation variable. So from equation 2, okay, where's equation 2? I have equation 2 here. I can just bring my equation 2 down there and put it in terms of deviation variable. Okay, so I have Q1 prime and H1 prime. And then let's take from equation 3. Let's get equation 3. This is equation 3. Let's bring it down there and put it in terms of deviation variable. So I will have A1 D H1 prime Qi prime. This is H1 prime. So this is my equation number 4. Okay. Is it number 4? I don't think so. I think this is equation number 4. This is equation number 5. Okay. Alright. So now you have two equations in terms of deviation variable for tank 1. The next thing you do is you need to take the Laplace transform of both equations. Take the Laplace transform. So you can do this quickly. 4 and 5. Okay. So from equation 4, the Laplace transform is, let me put it properly. Equation 4, I will have Q1 prime equals to Laplace transform of 1 over R1 H1 prime. And these are just equations. So you will have Q1 prime of S equals to 1 over R1 H1 prime of S. And you can rearrange this in terms of output over input for your transfer function. So the output is outflow from tank 1, which is Q1 prime over the height, H1. This is equals to 1 over R1. Okay. So this is your first transfer function. Let's say this is equation number 6, because at the end of the day, what you want is Q2 over Qi. Okay, let's proceed with equation 5 just now. You also need to take the Laplace transform. Where is my equation 5? Okay, I have it here. You can bring that down. And okay, so let's take the Laplace transform each term. So transform. Okay, so the left hand side is your derivative. So for derivative, what you have is S H1 prime of S minus the H prime of S at 0. Okay, so this one, this the right hand side, this is just equation. You have Qi prime of S minus 1 over R1 H1, which is a function. Okay, so we remember that the initial condition is 0. So then you can rearrange your term. So you have A1 as H1 prime of S plus 1 over R1 H1 prime of S equals to Qi prime of S. Okay, so what you need to do next, you need to rearrange your terms. So you would have H1, which is basically the output in terms of the transfer function. You have inlet, you have inflow from Q1, so that would be your input, and the result of the inflow from Q1 is the level in tank number 1. So this is Qi prime of S, and this is equals to R1 over A1 R1S plus 1. Let's put this in a standard form. I hope you remember standard form of transfer function. Your transfer function is K over tau S plus 1. So if you were to put this in terms of standard form, it will become K1 tau 1S plus 1, where now you can identify what is K and what is tau. So K1 is R1 and tau 1 is A1 R1. So this is another transfer function that you have. Okay, so let's put this. Just now you have equation 6. Now let's put this as equation 7. Okay, you have another tank, so you need to repeat the same thing for tank number 2. Let's do for tank number 2. Okay, for tank 2. Alright, let's do for tank 2, and tank 2 is just a repetition of what you do for tank 1. So you are using the same equation. So you can see equation number 8 is the mass balance equation, and equation number 9 is the equation for the resistance of the valve. It's just that now your variable is for tank 2. And then you substitute equation number 9 into equation number 8. So this equation number 10 is what you have, all right? And then again, you evaluate equation number 10 at steady state. So you will have this equation here, okay? And then again, you put your terms, or you put your variables in terms of deviation variables. While you are doing tank 1, you already defined Q1 prime. It's just that I put it here again so that you don't forget, and we are still dealing with Q1 here, okay? So, and then you have Q2 prime, you have H2 prime, and also the derivative dH2 dt. So you put everything in terms of deviation variable. So from equation 9, you should have Q2 prime equals to 1 over R2 H2 prime. And here is the same thing, A2 dH2 prime. This is Q1 prime, this is H2 prime. And the next thing you do is you take Laplace transform of equation 11 and equation 12. So for equation 11, when you take the Laplace transform, this is what you have. Q2 prime S equals to 1 over R2 H2 prime S. So you need to rearrange this so that you have your transfer function Q2 over H2 prime S, and this is equals to 1 over R2. So this is another transfer function that you have. Okay, so let's say this is equation number 13. Okay, and then from equation 12, you do the same thing. You have your uh, equation in terms of deviation variable, and you take the Laplace transform, and when you take the Laplace transform, you end up with this equation, H2 prime over Q1 prime equals to R2 over A2R2S plus 1. So again, you need to put this in terms of standard form. So you have K2 over over tau2S plus 1. So you can actually define what is your K2. K2 is equals to R2 and tau2 is A2 R2. Right? So now the next thing you do is you put all of this transfer function. This is your last transfer function. You put this transfer function. Let's put this as number 14. Okay. Let's put that as number 14. So we are going to put all of this into our final equation, because remember, as I have repeatedly said previously, what you want is Q2 prime of S over Qi prime of S. And this is equals to H1 prime over Qi prime multiply with Q1 prime over H1 prime of S multiply with H2 prime over Q1 prime multiply with Q2 prime over H2 prime. So as you can see, each of this transfer function, this one relates the level of tank 1 to the inflow Qi. This one relates the outflow of tank 1 to the level in tank 1. And this one, it relates the level of tank 2 to the inflow Q1. And this one relates the outflow Q2 to the level of tank 2, which is H2. So mathematically, if this one you can cancel, right? And when you cancel, you can actually get to Q2 prime over Qi. But what we are going to do now, we are going to take all the transfer function that represent each of that. Okay. So let's take one by one the transfer function. Let's take from the very first one, the one that we have, which is this one. Okay. Oops, let's have that. So we have that for that. And then the second one is this one. the third one just now is this. And the last one is this one. Okay, all right. So what you need to do now is you need to multiply all of them. Okay, one thing you need to realize when you put your transfer function in terms of standard form, K1 is actually equals to R1. You have defined it earlier, right? K1 equals to R1 and K2 equals to R2. So you can actually put this R1 here. This is actually 1 over K1 and 1 over R2 is actually 1 over K2. So what you can do is you can simplify all of this to give you the final transfer function, which is 1 over tau 1s plus 1 multiplied by tau 2s plus 1. Right? So that's your transfer function for Q2 prime, the outflow from tank 2 to relating to the inflow of tank 1. So this is your final transfer function.